Good morning one and all. Today I am going to talk about the atomic structure in General Chemistry 1 paper of first UG students. I am Dr.S.Shailaja, Assistant Professor of Chemistry of the Standard Fireworks Rajaratnam College for Women. A black body is an ideal physical object which absorbs all the radiations falling on it irrespective of the frequency and the angle of incidence. Of course, a good absorber is a good emitter, and it emits maximum energy at a particular temperature when compared to other objects. And the radiation emitted by a black body is called a black body radiation, and a German physicist Max Planck studied the black body radiation and he has proposed the Planck's law, and the Planck's law explains the electrical density of the black body radiation. And there are two main properties of this black body radiation. A black body is an ideal emitter and it is also a diffuse emitter. It is called as an ideal emitter as it emits almost all the energy it has absorbed and it is also called as a diffuse emitter as it is emitting the radiation isotropically. That is, radiation is emitted in all the directions uniformly. And a curve is drawn by plotting in the electron density on the y-axis and wavelength on the x-axis, and these curves are called the black body curves. And there are three characteristics of the black body curves. First one is at any particular temperature you will have a maximum wavelength at which the energy density is maximum. Now you can see in this graph that at 3000 Kelvin and you have a lambda max, and at 4000 Kelvin you have another lambda max, and at 5000 Kelvin another lambda max. And you can very clearly see that the position of the wavelength lambda max shift towards the lower wavelength. When comparing 3000 Kelvin and 4000 Kelvin, the lambda max of 4000 Kelvin is shifting towards lower wavelength. And when we are comparing 4000 and 5000 Kelvin, the wavelength of the 5000 Kelvin is shifting towards the lower wavelength side. And at higher temperatures, the maximum is more pronounced. You can see in the diagram that for 5000 Kelvin, the maximum wavelength is more pronounced. And for a black body, the emissivity epsilon is taken as 1. What is this emissivity? Emissivity is nothing but effectiveness in emitting radiation as thermal radiations. And Wilhelm Wien, he has studied the black body radiation and he proposed the Wien's displacement law, and often called as a Wien's law. The law states that the lambda max is inversely proportional to the temperature. So when we multiply lambda max and the temperature, we get a constant called a Wien's constant, which is B, and the value of B was found to be 0.0029 meter Kelvin. Now we will see a small problem, and in this problem you are asked to find out the temperature of the sun by assuming the sun as a black body. And your wavelength is given, and it is given as 0.475 micrometer, which is 0.475 into 10 power minus 6 meter, and it can be taken as 4.75 into 10 power minus 7 meter. And by using the formula of the Wien's displacement law, we are calculating the temperature of the sun. Max Planck found that using classical physics is not sufficient to explain the black body radiation, and so he used quantum theory to explain the black body radiation. And there are three postulates for this quantum theory, and black body emits radiation or absorbs radiation in small packets called the quanta. And you can see in this diagram that the first curve is a continuous curve and the second one is discrete. It is discontinuous here and there, and these are called photons. Now the energy associated with each photon is calculated by E is equal to h nu, and we know that nu is equal to c by lambda, and when we substitute we will have E is equal to h c by lambda. Here h stands for the Planck's constant, c for the velocity of light, and lambda for the wavelength of the radiation. And the black body also emits radiation as either 1 h nu, 2 h nu or 3 h nu, and you won't have any fractional values. That means it emits or absorbs radiation only as whole number multiples and not as fractions. And I have again a small problem for you. In this problem you are asked to calculate the energy and the wavelength is given. So we go in two steps. First, in the first step we calculate the frequency. We know the formula for the frequency, nu is equal to c by lambda, and by using c is the velocity of light, which we know 3 into 10 power 10 centimeter per second. And then the second step we calculate the energy by using E is equal to h nu after calculating the frequency. Now the final unit is ergs for us, and the energy can have units as joules and calories also, and if you are substituting in SI unit you will get the value as joules for energy. And J.J. Thomson in his experiment found that when radiations are falling on a metal surface, electrons are ejected, and when a strong beam of light of sufficient frequency striking a metal surface, it emits electrons, and these electrons are called the photoelectrons. And this is a photoelectric equation which is given as E photon is equal to 5 plus E electron. And each and every metal has its own threshold frequency, which is the minimum frequency that must be supplied to take away the electron from it. So the E photon, the energy we supply, is used for overcoming the threshold frequency or the energy, and then the remaining energy is used by the electrons to move. So that is taken as a kinetic energy. So E photon is equal to 5, which is nothing but the work function, plus E electron. E electron is nothing but the kinetic energy of the electron. And here we know that, and V square, in this V stands for the kinetic energy of the electron. Now we will solve a small problem regarding this. In this problem you are asked to calculate the energy, the kinetic energy and the velocity of the photoelectron, and you are given the wavelength of the photon to be 4000 angstrom, and work function is given, it is 2.13 electron volt. So first we calculate the energy of the photon, then we calculate the kinetic energy, and then as velocity. And remember, you are asked to calculate the energy in terms of electron volt. So in order to calculate the energy in terms of electron volt, we have to use this conversion. 1 electron volt is equal to 1.602 into 10 power minus 19 joules. So this is a way how we calculate problems in photoelectric effect. Thank you one and all. I hope you all are benefited by viewing this module, and we will meet in the next module. Thank you.